Good morning, dear students. Welcome to Deeksha Online. Today, we are going to discuss some problems with respect to aldehydes, ketones, carboxylic acids, and polymers. Let us take the first example. Identify the product in the following reaction. So, we have given a reactant, and the reagent is hydrazine with KOH and water. So, basically, it is based on Wolff-Kishner reduction. So we'll take the solution first and then come back to options. The reactant given is, we have a benzene ring, one chlorine, and you have one COCH3 group, and we have one NO2 group, and another cyclic ring, and attached to that we have one cyclic acetal structure. So this is the reactant. So we know that NH2, NH2 and KOH is Wolff-Kishner reduction, and Wolff-Kishner reduction is reduction of carbonyl group to CH2 group, direct reduction of aldehydes and ketones to corresponding hydrocarbons. So definitely this ketone group what we find here will be reduced to CH2, CH3. The point is which other groups can get affected by this basic medium. So NO2 is there at para position with respect to chlorine. So this chlorine can be replaced by hydrazine, the nitrogen nucleophile part, through SNAR mechanism. Because of nitro group present, chlorine can undergo nucleophilic substitution in basic medium. And also the acetal what we find here, ether structure is stable in basic medium, so that won't get disturbed. So product should be like this. You have same benzene ring and I have the same cyclohexane ring. The acetal part will remain as it is. This NO2 is also not disturbed, but this COCH3 will become CH2 CH3 and this will become NH2, or it can be replaced even with KOH. So R NH2 NH2, or that's a nucleophile. Even it can be replaced by directly with OH. So I can get even OH also. Either of these two should be there in the options. Now we'll go to the options. So you can clearly see they have taken OH as a nucleophile to be replaced. So option B, you can see the cyclic acetal structure as it is. Chlorine is replaced by OH and this has become CH2 CH3. Option B is the correct answer. So remember, in Clemenson's reduction and Wolff-Kishner reduction, the groups which are disturbed by the acidic or basic medium will also get reacted. So we need to select a suitable reagent depending upon whether we have acid sensitive group or base sensitive group in the given reactant. Example 2. Identify the product D in the following reaction. We have a sequence which you have to solve. So we'll go to the solution first and then come back to option. The reactant first given is cyclohexane with one OH and other one CH2OH. The first step is PCC. If I take excess PCC, both alcoholic group can be oxidized. Secondary alcohol get oxidized to ketone, primary alcohol get oxidized to aldehyde. Then the second step is reaction of glycol in H+, and we are using only one equivalent, so it will react either with aldehyde or ketone. Aldehyde is more reactive towards nucleophilic addition, so it will react with aldehyde to form cyclic acetal. So ketone will remain as it is and this will become cyclic acetal. So we have protected the aldehyde group from the reagent which is used in the next step. Now next step is CH3MgI. So CH3MgI will now attack only ketone. So I'll get this as the product. OMgBr CH3, and this cyclic acetal will remain as it is. So when you hydrolyze this, hydrolysis step is also there, it becomes OH, this becomes CH3, this will again come back to CHO. And next step is NABH4. So we are reducing with NABH4. So the aldehyde get back to CH2OH. So the secondary alcohol has been converted to tertiary alcohol and the primary alcohol will remain as it is. This should be the end product D. So we will see the options. So you can see clearly CH2OH and CH3 and OH, this is become tertiary alcohol, and CH2OH is there as it is, and option C is the correct answer. Go to the next question. Example 3. Identify the product C in the following reaction. So options are given, we have to work out the sequence. We'll go to the solution. The sequence is cyclopentanone. First reaction is HCN. So it is nucleophilic addition. So this will become OH and CN. Now the next step is lithium aluminum hydride. Lithium aluminum hydride can reduce cyanide to primary amine. C triple bond N becomes CH2NH2. OH, then CH2NH2. Now after this LiLH4 step is HNO2. HNO2 is diazotization. So in case of aliphatic amines, the diazonium salt will be unstable. So first it forms relatively less stable diazonium salt CH2 N triple bond N plus and Cl minus. So this N2 goes out, loses nitrogen, forms the carbocation. So now the carbocation has to undergo ring expansion to gain more stability, but you have OH group also along with that. So OH group can push the electron pair to have the ring expansion. As a result, it is like pinacol, pinacolone rearrangement becomes cyclohexanone. This is the end product. So option we'll see once. So end product is cyclohexanone, 5-membered ring has become 6-membered ring. So option should be A. We'll go to the next question. Example 4. What is the correct order of reactivity of the following compounds towards nucleophilic addition reaction? So we'll go to the solution part. As we know, the nucleophilic addition depends on two factors. One is steric factors, other one is electrophilicity. And aldehydes are more reactive than ketones. So what are the compounds we are given with? So we have benzene ring in all the compounds and attached to that one cyclohexane ring. So first one there is a ketone group, and the second one we have benzene with cyclohexane ring, same ketone, but there is one NO2 group attached to benzene ring. And third one we have same structure, ketone again, but we have methyl group. And the fourth one we have benzene ring nitro group with aldehyde. So aldehydes are more reactive than ketones because of steric factors, and also you have nitro group in the same compound, so electron withdrawing effect is also there. So fourth compound should be first in the order of reactivity because of it is an aldehyde. Now remaining three are ketone. So the steric environment is more or less same ketone group, but there is one NO2 group in the benzene ring at ortho position, so it will increase the electrophilicity at the carbonyl carbon. As a result, the NO2 group 1 becomes second, without any group becomes third, and methyl group 1 becomes fourth. So answer should be, if I say call this as 1, 2, 3, 4, it should be 4 greater than 2 greater than 1 greater than 3. This should be the order of reactivity. So we'll go to solution. So answer should be 4, 2, 1, 3. Option C. We'll go to the next question. Example 5. Again, identify the end product C in the given reaction sequence. So we have to go for the solution. We'll take the solution, then come back to options. So the given sequence is, we have cyclohexane ring, and you have one alcoholic group here. Then second side chain you have one more OH and CS3, and one CS3 is here. This is the compound given to us. So first step is PCC excess. So both the alcoholic group converts into corresponding ketones. So you get ketone here, this CS3 will remain as it is, and this becomes COCH3. So the next step is given as Br2 NaOH. So Br2 NaOH for a ketone, it's haloform reaction. So since there is methyl ketone here, it can undergo haloform reaction. So eliminates CH-Br3, and this ketone become carboxylic acid. So first ketone will remain as it is. This become COOH, and methyl will also remain as it is. Then next step is given as heating. In case of this, if I take this is a carboxylic acid group, this is alpha carbon and this is beta carbon. So the beta keto acids undergo decarboxylation very easily to lose carbon dioxide, and it will become just a ketone. So CO2 is going out, becomes methyl cyclohexanone. So answer, we'll go to the option to see the answer. So answer should be B. Go to the next question. Example 6. Which of the following will form stable hydrate? So all of you know hydrate means jump diols. So jump diol stability we have to check. We'll go to the solution part. So jump diol stability is affected by mainly two factors. Presence of electron withdrawing group. So jump diol stability depends on electron withdrawing groups and strain, angle strain in the ring. In cyclic ketones, so we know in cyclic ketone, cyclopropanone can be existing as jump diol very easily OH and OH compared to cyclohexanone converting into gem diol. So here what happens, because of the strain increase from ketone, this has more strain than this one. So this is stable. Here there is no strain, so gem diol will convert into ketone easily. So this is more stable. In this case, ketone is more stable. So these are the two factors affecting the stability of gem diol, presence of electron withdrawing group, and strain in the cyclic ketones. So if I see the given options, first one is given benzene. There are 3 keto groups. So if you make this as hydrate in aqueous medium, the central ketone group can convert into gem diol, because there are 2 electron withdrawing group very strongly, so that the central ketone can become gem diol, which is very stable. The second compound also in the same way, this is a triketone. So again the middle ketone will become gem diol. Like this, the middle ketone becomes gem diol, and 2 ketones are acting as very strong electron withdrawing group. And the third one, what we saw already, the cyclopropanone in aqueous medium water, it can convert into gem diol easily. And the last one given is cyclohexanone with only 1 ketone. There is no electron withdrawing group. This is unable to convert into gem diol. This will be least stable, because there is no electron withdrawing group, there is no strain, so the gem diol is unstable, the keto is only more stable. So option A, B and C, all 3 will form stable hydrate. So answer should be A, B and C. We'll go to the next question. Example 7. What is the product in the final reaction? X major compound we have to find out. So we have given cyclopent 1,3 diene with acetone. Medium is sodium ethoxide and ethanol. We'll see the solution. So we are given with cyclopent 1,3 diene, and in the medium I have ETO minus ETOH. So ETO minus, as we know, it is a very strong base, and in cyclopent 1,3 diene there are 2 hydrogens here which are quite highly acidic. Because of the proton, if you lose in that position, we get a carbanion which is a aromatic carbanion. So the acidic strength of these hydrogens are more, so this will take the proton. So I can say minus ETOH, so you'll get the nucleophile like this. Now this nucleophile can attack acetone. So nucleophilic addition can happen. So what do I get? Cyclopentane with 2 double bonds, and this will be attached to carbon and OH, then CH3 and CH3. So this is the end product of the reaction. So we will see the options. Option A should be the answer. Next question, example 8. Which of the following is not formed during the reaction? There is a sequence given. We have to go through the solution for the sequence. So we have given with benzene, CH, double bond, CH, CH3. So cis or trans will not matter much. So it is given Hg2 plus H plus and water. So acid catalyzed hydration of alkyne. Alkene, mercuration, demercuration. So what happens? You get an alcohol, right? So mercuration, demercuration, HgOAc twice, H2O, then acidic hydrolysis we can do. So you get alcohol. So the reaction follows Markovnikov addition of water. So Markovnikov addition means the positive charge is more stable at the benzylic position. So I'll get OH here and CH2, CH3 here. Now next step is PCC. So the alcohol becomes aldehyde, ketone. Then you are reacting this with NH2OH. NH2OH means it forms oxime. NOH. So it can form syn and anti-oximes. Then first, after this, the step is acid medium. So it undergoes what is called as Beckmann rearrangement. So we'll see the solution for Beckmann rearrangement part. So we have benzene and ethyl in the oxime. So the same compound I'll take now, benzene, carbon, C2H5 ethyl group, double bond N OH. If I take this, if I take the H plus, so migratory group is benzene now because OH is here, anti group is this. So this will migrate to nitrogen. So I'll get the amide as C2H5, C double bond O, NH, pH. So on hydrolysis of this further, this can break. So it forms CH3, CH2, COOH plus pH NH2. This is one set of products possible. So propanoic acid and aniline are the two possible products with this particular isomer. If I take the other isomer, what will happen? So same benzene ring I am taking, carbon, C2H5, double bond N, now OH is this side. Now the ethyl group migrates. So ethyl group migrates means benzene ring will be with the carbonyl group NH, CH2, CH3. Now on hydrolysis of this will break. You get benzoic acid plus CH3, CH2, NH2. So ethyl amine and benzoic acid is the product formed. So four products we got. One is benzoic acid and ethyl amine. The other one is propanoic acid and aniline. So we'll see what compounds are given, what compounds are not given in the options. So we see clearly benzoic acid is present, so this will be formed. And see, benzyl amine is not formed, aniline is going to be formed, propanonic acid is formed, and ethylamine is also formed. So it's going to be answer is B because they're asking for not formed. So answer should be B. Example 9. Identify the major product in the following reaction. So we have given a compound having aldehyde group and ketone group and NaOH. So something to do with aldol or Cannizzaro reaction. We'll see the solution, then come to the option. The reactant given is, we have one benzene ring and aldehyde group is present, benzaldehyde group. In the ortho position, you have a side chain having a ketone group. So when I take NaOH as the base, so there is a possibility of either aldol or Cannizzaro. So the requirement for aldol is presence of alpha hydrogen in the molecule. So the molecule contain alpha hydrogen at two positions. So one here and one here. Since there is a benzaldehyde also one more carbonyl group, so it is an intramolecular aldol condensation. So if I number the compound groups containing 1, 2, 3, 4, 5, 6 and 7. Just for writing the product, I am numbering. So I have alpha hydrogen atoms at 5 and 7. And I can move the carbanion formed at 5 to aldehyde group, which is because aldehyde is more react towards nucleophilic addition. So if I move 5 to 1, if I write the product 5 to 1, so the product will be like this. There is 5-membered ring formed. So this is 1, this is 2, this is 3, this is 4, this is 5. So 5 has joined 1, 1 will have OH and 5 will have COCH3, that is 6 and 7. So on heating this loses water, so I can get benzene, 5-membered ring, COCH3 with a double bond at alpha beta position. This is one of the possible product. So in intramolecular aldol condensation, generally 5-membered and 7-membered ring will be formed as products. So other one is 7-membered ring. So 5-membered or 6-membered ring will be the stable product. 7-membered ring is not very stable. So the major part has to be 5-membered ring. So we'll see the other one also. So the compound again I'll write. Now what happens? This will attack here. So I'll be getting benzene ring. Attach that 1, 2, 3, 4, 5, 6, 7-membered ring. 1, 2, 3, 4, 5, 6, 7. Yep. So the again OH is here. Then this is CH3, you will have ketone here. So on heating, I'll get okay, sorry, why it is become 6-membered. Yeah. I'll write here. One, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah. This is joined. Ketone will be here. Double bond will come here. Ketone will come here. This is the product. So this is minor. 7-membered ring will be minor, and 5-membered ring will be major. So we'll go to the solution options. So in the options you can see the product what we wrote for this one, this is the answer for the question. Even this is font, but this is minor. They are asking for the major product, so this is major. Option B, oh sorry, option B, you have COCH3 next to it. So this is not alpha beta unsaturated, A is not the answer, so B is the major. Okay, answer B. Example 10. Which of the following alkene is not obtained in the following reaction? So we'll go to the solution sequence. The reaction is actually Wittig reaction. So I'll take the reactant what is given. So PH, CH3 and Br. So first we are reacting this with triphenyl phosphine. So what happens is it will form quaternary phosphinium salt. So PH, CH3 attached to this, Br will go PH3 plus and Br minus. So we have a hydrogen here. Now the next step is CH3Li, very strong base, minus and plus. So this strong base will take the proton, move the electron pair here to form the halide. So what do I get is PH, CH3, double bond, P, PH3. This is the halide which is formed. Now the next step, this halide is reacted with acetophenone. So I'll write in the next slide. So I had the halide as PH, CH3, double bond, P, PH3. The other compound I can write same PH, CH3, double bond O. So what happens is cyclic intermediate is formed. So this pair of electron will come here and this electron pair will go here. So I'll get C, C, P, PH3, then O. This is a cyclic intermediate. So this will have PH and CH3. This will also have PH and CH3. The cyclic ring breaks depending upon the orientation. You can get both cis and trans alkenes for the compound, though it is syn elimination. So it's going to be syn elimination. Like this, it will go eliminate, cyclic ring breaks. So loses PPH3O and forms CH3, CPH, double bond, CH3, PH. Plus I can get even trans isomer also. So the orientation, how the ketone is forming the cyclic intermediate, it will decide whether cis and trans both are possible. Definitely both are possible. And PPH3O, phosphorus oxy triphenyl will be eliminated. P double bond O, PH3 is eliminated. So this is one of the important reaction in aldehydes and ketones, Wittig reaction giving alkenes. So we'll go to the solution, the options. So the options are, you can see very clearly, PH, PH, PH and trans. So this is possible. Here PH, PH is cis, which is also possible. Both PH cannot be attached to same carbon. This is not possible. And this type of alkene is not possible. So option C and D are not obtained. A and B are obtained. Example 11. Which of the following is the correct order of reactivity towards benzoin condensation? So, benzoin condensation is a nucleophilic addition reaction in the first step. So, we can see the reactivity of the compounds. We have been given all benzaldehydes, benzoin condensation. So, benzaldehyde should be the product, should be the reactant. So, in the first one we have methyl group. In the second one I have NO2 group. In the third one I have OH group, and the fourth one I have two groups. One is CS3 and meta we have nitro group. So, if I take the reactivity is going to be increased if there are electron withdrawing group, especially at ortho and para position. So, among these, nitro group is very strong electron withdrawing at ortho and para. This is the number 1 in terms of reactivity. Then second one, we have methyl group at para in both the reactants, but this has one extra nitro group. So, there, even though it is at meta, relative to compound number 1, this is more reactive. So, this is the second one. And the third one, obviously methyl group, and OH is a plus R group. It is a activating, or I can say it is electron releasing group at para position. So, this will be the least reactive in terms of reactivity. If I call the compounds as 1, 2, 3, 4, answer should be 2 greater than 2 greater than 4 greater than 1 greater than 3. This should be the option. So, we will see the options. So, you can see clearly 2, 4, 1, 3, option C is the answer. We will go to the next question. Example 12. Identify A and B in the following reaction. So, it is given as C5H10O aluminium ethoxide. So, aluminium ethoxide, and given very clearly Tishenko reaction. The ester what we get is hydrolyzed to get carboxylic acid and alcohol. So, these two are the compounds what is obtained. So, we will work it backwards to get the corresponding compound. These are the options. We will go to solution part. So, the Tishenko reaction is basically, if I take the general reaction, RCHO, 2 molecules are required. If I react this with aluminium ethoxide, one molecule undergo actually oxidation. To write the product, I can write RCOOH, oxidized molecule. The other one get reduced, RCH2OH. So, actual product is the ester of these two. So, compound should be RC double bond O OCH2R. This is Tishenko reaction. Okay. This is a general concept of Tishenko reaction. So, this actually acid and alcohols are not formed. It is directly forming ester as the product. This is just a logical approach what I have given to write the product. Now, in the given question, what are the acid and alcohol given to us? The acid and alcohol given to us are, this is the acid and this is the alcohol. So, we can clearly see this is oxidized and this is reduced. The aldehyde which gives this compound should be this one. So, this on oxidation gives this compound, this on reduction will give this alcohol. So the compound A should be aldehyde. So you can see 1, 2, 3, 4, 5, C5H10O. This is compound A. Now we'll write the Tishenko product for compound A. So the compound A is now aldehyde is like this. So the oxidized product I'll write separately here, COOH, and the reduced product I'll write from the opposite side. So 1, 2, 3, 4. Okay, so this is say OH, 1, 2, 3, 4. This is the compound. So this is reduced product, this oxidized product, remove water. So you can connect the compound. So the ester should be ALOET thrice. So I'll write the first acid part. Sorry. So I'll write the product here. This is methyl, this is acid, ester. After that we have 4 group, 4 carbon atoms. This will be the methyl. So this is the ester. So this is compound B, which is an ester. We'll see the solution, the option. So you can see the option A, this is aldehyde, and ester 1, 2, 3, 4. So this is correct. A is correct here, and here this CH3 portion is incorrect. So A is the correct answer. B and D, B will not be the correct answer. Though compound A is correct in the B option, compound B is incorrect in the B option. So option A is the right answer for this Tishenko reaction. Example 13. Identify the number of OH groups present in the product for the following reaction. So we'll go to the solution part. It's an integer type question. See, the concept is very important here. It's a combination of Aldol and Cannizzaro reaction. The concept is very much to be asked in advance. The same concept based question appeared 3 to 4 times in 3 consecutive years. So one of the very important concept for advanced examination. So you have one aldehyde and one ketone, and you are reacting this excess of HCHO. So whenever we use excess HCHO and base, it is a combination of both Aldol and Cannizzaro reaction. So first steps will be Aldol condensation. Number of alpha hydrogens present, all those alpha hydrogen present will be lost and becomes carbanion and undergo cross Aldol condensation with formaldehyde, because formaldehyde is exclusively highly reactive for nucleophilic addition. So in this molecule we have one alpha hydrogen here and one more alpha hydrogen here. So both of these alpha hydrogens are replaced by CH2OH group. The first thing what you have to do is all the alpha hydrogen present in the molecule should be replaced by CH2OH groups. This is the first step. Now the molecule will not be having any alpha hydrogen. Now it undergo cross Cannizzaro reaction. So remember, in a cross Cannizzaro reaction, when we have formaldehyde in the system, always formaldehyde get oxidized, the other compound has to get reduced. So whatever the carbonyl groups present in the given reactant will convert into alcohol, because formaldehyde is getting oxidized to formic acid. So this is Aldol steps, and this is Cannizzaro. So what do I get as a product is benzene ring. So CH also becomes CH2OH. This already one CH2OH. This is CH3, CH2OH already there, and this also become OH. So there are 4 OH groups present in the given product. Now how to write the product directly? So whatever number of alpha hydrogens are present, all those alpha hydrogen to be replaced with CH2OH groups. The second point, whatever the carbonyl groups present in the molecule should be converted to corresponding alcohols. Then count the number of OH groups present in the given product at the end. So as per the given molecule, answer should be 4. So answer is 4. Next example, example 14. Identify the major product in the following sequence. So the options are given. We'll go to the solution first. The given compound reactant again has a benzene ring and one CH3 group, that is toluene, then one isopropyl group is present. So we are reacting this with one equivalent of NBS. So NBS will always be free radical mechanism, substitutes at benzylic and allylic position. So benzylic position, here there are 2 benzylic positions. The most stable one is a tertiary benzylic. So bromine goes to isopropyl group. So the first product is this. Then after that it is done with magnesium and ether, and then it is reacted with carbon dioxide. So carbon dioxide, you take RMgX become RCOOH. So RBr will become RMgBr, then finally RCOOH. So Br is finally replaced by carboxylic acid group. This is the final product. So we'll go to the options. So option C, if you take this is not possible. CH3 can never be replaced, it's not possible. So you can see here clearly this is one more carbon is introduced, and tertiary, this is the correct answer. Option D is the right answer. Example 15. Which of the following has lowest pKa value? So here only we can make out. So basically you can see the carboxylic acid group is attached to sp3 carbon here, and here it is attached to sp2 carbon, and this is benzene, that's also sp2 carbon, and this would be sp carbon. So sp carbon being highly electronegative, the carboxylic acid group will have more acidic strength. It's because electron withdrawing group minus I effect and minus R effect will increase the acidic strength of carboxylic acid. So option D will be the one with highest acidic strength, or I can say lowest pKa value. Lowest pKa value means low pKa, higher acidic strength. So option should be D. We'll go to the answer. Answer is D. Example 16. Which of the following is incorrectly matched with the following products? So we'll see one by one in the solution. The first one is given cyclohexane ring with one double bond inside and carboxylic acid. Reacted with SOCl2, so carboxylic acid should become acid chloride. So this is the product for the first one, and the second one, double bond COOH and it is given lithium aluminium hydride. Lithium aluminum hydride can reduce acid derivatives, aldehydes, ketones, everything to primary alcohol, but double bond will not be reduced. So double bond to be reduced, it should have beta aryl group only. Then only alpha beta unsaturation with respect to aldehyde or a ketone can be reduced by lithium aluminum hydride. So here the double bond is not going to be reduced, only as acid will be reduced to alcohol. This is the second one. The third one, same kind of reactant, you have cyclohexane with one double bond and MgBr. So MgBr, when you react with carbon dioxide, that should become carboxylic acid. This is the product for the third one. And the fourth one, given COOH on heating is becoming cyclohexene. So if I take carboxylic acid, this is alpha, this is beta. So beta unsaturation is present. Like beta keto acid, this can undergo decarboxylation very easily. So if I write the reaction over there for that, this is acid, this is unsaturation. So this will go here, this comes here, this goes here. So the H will come over here, minus CO2, I will get double bond here, cyclohexene. Okay, so beta unsaturation need not be only beta keto, beta unsaturation can also answer decarboxylation. So we'll see the options now. So if you see the options now, in the option A, this is correct. Option B, you have double bond is reduced, which is not correct. And option C also correct, and option D is also correct. So answer should be B for this particular question. Question number 17. How many moles of NaOH is required to neutralize the following compound in aqueous medium? So if you see here only, carboxylic acid is one acid group which requires sodium hydroxide for neutralization. So this is 1. Sulfonic acid is the first one to be neutralized. So this is also 1. Now you have CONH, 2 strong electron withdrawing group. This hydrogen is also very acidic. This also requires another 1 mole of NaOH. Then phenol will take 1 mole of NaOH because phenol can be neutralized. It's more acidic than water. Definitely phenol requires 1 mole of NaOH for neutralization. But alcohol in aqueous medium, very clearly mentioned, alcohol not neutralized in aqueous medium, because alcohols are weaker acids than water. In aqueous medium we cannot neutralize alcoholic groups. So as a result, the answer should be 4 moles of NaOH. We'll go to the answer key. Answer should be 4. Example 18. Identify the major product in the following reaction. So we'll go to the solution. The given question is, you have a benzoic acid molecule with methyl, and one more reactant is one more benzene ring, CH, single bond, N triple bond N with a plus and a minus sign here. Now if you see the structure of the second reactant, it is very similar to diazomethane. So in case of diazomethane, CH2, N triple bond N plus and minus. This is diazomethane. So diazomethane, if I use for carboxylic acids, or C double bond O, OH, not acid chloride, I am using for carboxylic acid. it will undergo what is called as methylene insertion. So the N will go out, nitrogen is lost, and S becomes RC double bond O CH3. So you have to introduce between OH bond, make it as a methyl ester. So same thing we have to do for this also now. So if I take the given reaction, so the reaction was methyl group C double bond O OH plus benzene ring CH single bond N triple bond N plus and minus. So this nitrogen will go out, this to be introduced between OH bond. So you are going to get this product CH3 double bond O. This will become CH and one more H is there, CH2 and one benzene ring. So this is the product what we should get as an ester. So we'll see the options. If you see the options, so you can see CH pH is given as pH, COOPH. This is the A is the correct answer. If you see B, it is not CH3, pH can never come here, impossible. Here also it is not possible, and this is change the entire carboxylic acid structure, which is also wrong. So option A is the only possible product in the given answers. So remember CH2N2, any diazomethane or both hydrogen of diazomethane can be replaced by different groups. Always it is getting inserted between OH bond to form corresponding esters. Example 19. What is the major product of the following reaction? We will see the solution and then come back to options. So in the given question we have anhydride, cyclic anhydride, and we have an amine reacting. So cyclohexyl amine. So it's a nucleophilic acyl substitution. So this will be reacting here and this gets separated. So what do we get? Oh sorry, this is no more ring. So this will be CO, NH and cyclohexane ring, and 1 2 3 4 1 2 3 4, this will become carboxylic acid. So second substitution is very unlikely because NH, that is not an amine now, it is an amide. Nucleophilicity of the nitrogen atom is very much decreased in amide, so it cannot initiate another acyl substitution. So it will become the COO minus will become carboxylic acid and form this as the final product. We will see the options. If you see the options here very clearly, CONH cyclohexane ring and 1 2 3 4 forming carboxylic acid group. Option A is the right answer. So option B is difficult to form because the nitrogen atom of the amide is not having that much nucleophilicity to form the second substitution and form the compound B. So C and D are totally irrelevant. So option A is the answer. Example 20. Identify the missing reagent in the following reaction. We'll see the reaction, solution, come back to options. The given question is based on Claisen ester condensation. So you have ketone also can take part in it. So I have cyclopentanone. We know alpha hydrogens are acidic. So if I react this with ETO minus, loses ETOH This is the alpha hydrogen, let us say. So this is going to be abstracted. So what do I get? A corresponding carbanion, which is stabilized by resonance through enolate. On this carbanion, to introduce COOET, I have to take this compound, diethyl carbonate, CO3 2 minus, you can see, and two ethyl groups are there. So this will attack here, and the acyl substitution takes place. One of the OET is going out. So what do we get? Cyclopentane, ketone. This will become now C double bond O, OAT. So the compound I should take should be diethyl carbonate. So I'll go to the options. Option should be C. Example 21. Identify the product in the following reaction. So clearly you can see here Br2NaOH and primary amide. So the reaction is based on Hofmann bromamide reaction. So we'll go to the solution. The given reactant is having benzene ring, then CONH2, and here we have one wedge, one dotted line. Wedge has H, dotted line has CH3. So when you react with Br2NaOH, Hofmann bromide reaction, so you will get the intermediate NHBr, and the intermediate you are going to get like this: benzene, this is the intermediate what I'll get. Now what happens? This negative charge comes here to form the double bond. So this carbon here, this pair of bond migrates to nitrogen, eliminating Br. So this migration will be with 100% retention in configuration. So the amine what I get, isocyanate what I get, will also have the same structure. Isocyanate, so the H will still remain in the wedge, methyl will still remain in the dotted line. So when you hydrolyze this in basic medium, I get amine with the absolute same configuration. H still remains in the wedge, methyl group still remains in the dotted line. So this is the product what you will get, only one product, no other product. It is no racemization, no inversion, it is 100% retention. So only one product is formed, no stereoisomers. So we'll go to the solutions or options. So if you see the given compound, H and CH3 is in the wedge and dotted line. So in the compound, this cannot be CH2NH2, which is wrong. It should be NH2, H is in wedge, CH3 is in dotted line. Answer should be B. The other isomer is given here, which is not at all possible. Answer is B only. Example 22. What is the order of reactivity of the following acid derivatives in the following reaction if the group Z is? So the given reaction is clearly given: nucleophilic acyl substitution. So nucleophilic acyl substitution will depend upon the leaving ability of the group Z. So we'll take the solution. So in the reaction RCOZ, nucleophile minus, getting RC double bond O Nu plus Z minus. So this leaving ability will matter. Leaving ability proportional to reactivity. So what are the given groups? So first group is benzene ring with SO3 minus. Sulfonate ions are given for all of them. So sulfonate ion is a very good leaving group because sulfonic acid is relatively stronger acid. So sulfonate ion is a weak base and a stable base. So all are SO3 minus given. The difference is the groups present at para position. So one is not having any group, second one has NO2, the third one has CF3 and the fourth one has OCH3. So all of us know sulfonate ion is a negative ion. Electron withdrawing groups will stabilize the conjugate base. More the stability of the conjugate base, more will be the ability to leave because it becomes even more weaker base. So the one which is having very strong electron withdrawing group at ortho and para would be nitro group because minus R effect and minus I effect both will happen. So NO2 is the first one in reactivity. This is one. Next comes CF3, quite strong minus I effect but no resonance effect. So it is going to be second. Then OCH3 acts as a plus R group. It is destabilizing the sulfonate ion. So it is the least, that is fourth one. So third one has to be the first one. So answer according to this should be 2 greater than 3 greater than 1 greater than 4. 2, 3, 1, 4 should be the answer. So we'll see the options. Answer should be 2, 3, 1, 4. It is D. Example 23. What is the product in the following reaction? So we'll take the solution. The reactant given is, say, cyclohexane ring. You have two OMe groups and here we have COOMe ester groups. So just hydrolysis, acid hydrolysis. So all acid will ester become acid. So I'll be getting two carboxylic acid groups. Okay. Then ethers will become alcohol. OH, OH. Now one carbon having two OH group will lose water. So I'll get this becomes ketone here, COOH and COOH. And also it is given heating. So the carboxylic acid group have beta keto group. So alpha, beta, alpha and beta. So both the carboxylic acid group get decarboxylated and forms only cyclohexanone. That is the end product. So we'll go to the options. Option B. Example 24. Identify the product in the following reaction. So we'll see the solution. So in the given question, we have active methylene compound. So CH2, COOET, COOET. So it's an active methylene compound. These hydrogens are very highly acidic. So we have C2H5O minus as a base. So it will take the proton. So it becomes C2H5OH. So I'll get this as the carbanion, CH minus COOET, COOET. This is the first intermediate. Now we are reacting this with alkyl halide. So this will attack alkyl halide and undergo SN2 reaction, form the product. So it is going to be CHCOOET twice. So hydrolysis. So when I do hydrolysis, both ester will become acid, and heat, when you are doing two acids and one carbon, becomes monocarboxylic acid. So this will be COOCH to COOH. Then we are reacting with PBr3, that is PBr3 is like P plus Br2, so you have a possibility of HVZ reaction. So this CH2 whatever is there, that there is a substitution with Br. So PBr3 will get me this. Then this compound, when you react with NH3, this Br is replaced by COOH. So we'll take the other slide. I'll write from the previous step. This is the compound we had. So PBr3 is like P plus Br2. So it is going to be HVZ reaction. So Br will come here. So when you react this with ammonia, so HBr is eliminated, you are going to get NH2. Amino acid is obtained. This is the end product. So we'll see the options. You can see clearly. So NH2COH option C matches with the given requirements. Example 25. Identify the product in the following reaction. So a series of reaction is given. We will just work out that. The given sequence goes like this. You have acetylene, one equivalent of NH2, NaNH2. So one hydrogen will be taken out, CH triple bond C minus, then Na plus. Now this is attacking acetaldehyde. So this nucleophile attacks here, goes like this. So I get a product like this, CH3 CHOH, and this will be C triple bond CH. Now Al2O3 is the next step, dehydration. Al2O3, so there is no other hydrogen available with a triple bonded carbon, it has to take from CH3 only. So I will be getting CH2 double bond CH single bond C triple bond CH. Now you are adding one equivalent of HCl. When there is a double bond, triple bond, both are present, triple bond becomes more reactive. So CH2 double bond CH single bond C Cl double bond CH2. So with HCl it is going to give 2-chloro-buta 1,3 diene. That is nothing but chloroprin. And next step it is given, it is polymerized. So we had CH2 double bond CH C single bond Cl double bond CH2, then polymerize. So you get double bond shifted CH double bond CCl single bond CH2, and this goes on repeating. So chloroprin polymer should be neoprene. The final product is neoprene, which is an important polymer. So the solution, the answer should be neoprene. Answer C. Example 26th. Which of the following is formed by condensation polymerization process? It's a conceptual question. So if I see the polymers given, nylon 6,6 is a condensation polymer formed by adipic acid and hexamethylene diamine. Terylene is a condensation polymer formed by terphthalic acid and ethylene glycol. And glyptol is also a condensation polymer formed by phthalic acid and ethylene glycol. Orlon is also known as PAN, which is an addition polymer formed by acronitrile, CH2 double bond CH single bond CN. Acronitrile is the monomer which is giving polyacronitrile. It is also called as Orlon. So D is the only addition polymer. A, B, C are condensation polymers. It's a conceptual question. We'll go to the answer key. So answer is A, B and C. Question number 27. Natural rubber on reductive ozonolysis gives. So we'll go to the solution part first. Natural rubber is formed by isoprene. So what is the structure of isoprene? CH2 double bond C single bond CH3 single bond CH double bond CH2. So when N molecules are polymerized, what happens? The double bond gets shifted. So this will go here, this goes to another molecule, and some other molecule you get a bond here. So the partial structure is like this: CH2, this becomes single bond, C, CH3, this will be double bond, CH, CH2 joins to another molecule, right? CH2, C, CH3 and double bond CH and continues. So this is natural rubber. When you subject natural rubber to ozonolysis, the double bonds are broken. So if I take this compound, what is formed? This become aldehyde. So this becomes aldehyde, CH2, CH2, C double bond O, CH3. This is the compound what is formed from the natural rubber. So this is ketone of the second left hand side you take. This becomes ketone for the previous one, and this become aldehyde for the next product. So if I number this CHO, that is 1, 2, 3, 4, 5. So 4-oxopentanal. The product is 4-oxopentanal. So you can't take the isoprene converted to ozonolysis product. You have to polymerize, get the structure of natural rubber, then break the double bonds to get the ozonolysis product. So option should be 4-oxopentanal. So option should be B, 4-oxopentanal. Example 28. Among the following, the one with the strongest intermolecular forces. So this is also conceptual. So intermolecular forces are stronger for fibers, weak for elastomers. So neoprene is a rubber, so it is an elastomer. So this is not the strongest one. Polythene is thermosetting thermoplastics, which will have intermediate intermolecular forces compared to fibers and elastomers. Nylon 6 is a fiber, which is the answer for the given question. So fibers will have strongest intermolecular forces of attraction. So answer should be C. Question number 29. So it is a matrix match. So we can try to match here. So starch. Starch is condensation polymer of alpha D glucose unit. So throughout the structure you have only alpha D glucose unit. So it can be mapped for homopolymer and condensation polymer. So this can be mapped for homopolymer and condensation. So it should be P and S. Nylon 6. Nylon 6 is again condensation polymer of adipic acid and hexamethylene. Sorry, nylon 6,6 is that. Nylon 6 is also called as Perlon, which is a homopolymer of caprolactam. Caprolactam is obtained by treatment of cyclohexanonoxime with Beckmann rearrangement reaction. You get a caprolactam that is polymerized to get nylon 6. So it's a homopolymer and a condensation polymer again. So it is going to be again PS. Dacron. Dacron is terylene, is coming from terephthalic acid and ethylene glycol. So it is a copolymer and again it is a condensation polymer. So it should be Q and S. PVC is polyvinyl chloride, monomer is only vinyl chloride. So homopolymer, but it is an addition polymer. So PVC addition polymer, so I can match it to PR. So this is the matching for the given question. So PS, PS, QS and PR. Question 30. Which of the following statement is correct with respect to polystyrene? Polystyrene is used in packaging. It is also known as styrofoam in the form of thermocol, right? So it is also known as styrofoam. It is a correct statement. It is a perfect insulator, which is also correct. Used in packaging, that's also fine. Capable of showing geometrical isomerism because double bond is no more existing in polystyrene. Styrene is the monomer having a double bond. Even that is also unable to show geometrical isomerism. So here this also will not show geometrical isomerism. The monomer is CH2 double bond CH PH. So this cannot show geometrical isomerism. Polymer also will not be showing any geometrical isomerism. So this is a wrong statement. Answer should be A, B and C. A, B and C. Okay, so these are the questions what I thought I'll discuss with all of you in the chapters aldehydes, ketones, carboxylic acids and polymers. Thank you.